So this is the final webinar of the e-SafeFood project. So e-SafeFood is aiming at developing a comprehensive e-training program on microbial safety in food chains for current and future professionals. And it's co-financed by the Erasmus Plus agency. It has started in January 2022 and will end at the end of this month, November 2024. So this is a webinar about our two modules, control of microbial hazards and risk analysis. We will first have an introductory part with also the presentation of the platform by Luminita from the ISECI team. And then we will ask you to connect to the platform for the initial quiz. So it's very easy. I mean, I hope it's going to be easy for you. It's 7 questions. The quiz will be open until the coffee break, so you still have time in the morning to complete if you don't have time for the dedicated time to finish. Then we will present you 3 presentations on the control of microbial hazard module, 2 units on the basic level and 1 in intermediate level. So the 2 units of the basic are origin of microbiological contamination of foodstuffs and conditions for the proliferation of microorganisms and control measures. The intermediate level will be how to prevent and control process deviations. Then we'll have a coffee break, and we will then follow with the risk analysis module, which is only advanced level, so 2 units, risk assessment of foodborne pathogens and examples of exposure and risk assessment models. We'll have a time dedicated to questions if you have any. So during all the webinar, you are free to write the questions in the chat, and then we will check during the presentations if the speakers can answer the questions. So we can also take a few minutes before the coffee break if there is anything you would like to have explanations, or we can wait until the Q&A session. Then we will deliver you the results of the initial quiz, and we'll have a small conclusion.
Good morning, everyone. Also from my side, my name is Luminita Ciolacu, and I'm also a project manager working at the ACTIA Association. Thank you very much, Wilfried, for the nice introduction of the organizations and also of the learning program. I'm here now on the homepage of the Moodle platform. So this is developed by ISECI Food Association. And if you go here on the homepage and scroll down, you will see that at this moment we have some courses available. And you will find also the e-SafeFood training program. You have here the modules that Wilfried introduced to you, and also the overview. So if you click here, you will have some information about some general information about the modules. And as Wilfried said, we have added here the certification, and you will also find information on how to use the platform. So first of all, you need to create an account. You need to come here, and here if you see on the right side, for me it shows login, but you can also create an account by accessing. So for example, if you go to the microbial shelf life, you will see here the general description of the module and the levels that we have. For the basic level, we have the English version, but also French, Portuguese, and Spanish translations. And if you go further, then the platform will ask you to get an account, a student account, and you can do here at this step, in order to access all the materials which are available, you need first to create an account. So for me, I will just log in with my account. It's very easy. It's just some general questions that you need to fill in, and you will get your account very fast. Yeah, going back to the module, as I said, you can access each of the modules from here, and the structure of the module, of the modules is similar. I will go, for example, to the process validation. Here, you will have the general presentation of the module, to whom it was designed for, and what are you going to learn here. And for the process validation, we have only the advanced level. You can access here. For all the levels, you need to use the enrollment key, which is this one mentioned here in the description of the level. And going to the materials which are here presented, as Wilfried mentioned, this is an interactive learning program. It's organized in micro sessions and includes video presentation documents for the theory, as well as practical exercises and case studies to learn how to put all this theory into practice. So for the structure of this, you will see that we have a general information activity, and then we have the initial quiz where you can assess your knowledge before going through all the materials of the module. And then we have all this material organized in units. Each unit has different activity, and the activity has one or more documents, which can be, as I said, a video or an animation or a PowerPoint presentation, and so on. So the time for each of these activities is not very long, and you can do it as you consider as at your own pace. Each activity has a restriction step, so you cannot access the following one without doing the previous one. And at the end, after following all these units, for example, in this case, we have 3 units, you will have a final quiz to assess your knowledge. And after you finish the quiz, we will ask you also to give us some feedback in order to improve the learning program. And when you have filled also the assessment feedback form, you can download by yourself the certificate of completion. So this is very straightforward and intuitive, and you can do it by yourself in the platform. And yeah, this is similar for all of these modules that we have here. If you have any questions, just contact us. You will have the information in the overview page. Here you have our contact and also the contact of Wilfried. So, and we will be also here in the webinar. If you have any questions, we will be happy to answer them.
Okay, so let's start the presentations, and then we will come back to this. Or what do you think, Federica Luminita? Is it going to work now?
I think you can start with the presentation, and we will check to make sure that it's working, and we will let you know when this is fine.
Okay. Okay, so we will now ask Lisiane from Aerial to present 2 units. So it's in the control of microbial hazards module. It's basic level. This is unit 3 and unit 4. Let's start with unit 3 about the origin of microbiological contamination of foodstuff. So Lisiane, would you like me to share my screen?
Yes, please.
Okay. This is also a good way for me to show to participants how to access. So let's go back to the main page with the list of the 4 modules. Then we want to choose the control of microbial hazard module. Then you have the presentation of the module here with the 3 levels. We want to go to the basic level, so we click here. And then you have here you have 3 languages available: English, French, and Spanish. So I want to choose English, and then I have the presentation here of the different of this basic level. And then I have an initial quiz, which is not going to be interesting for us. You have Unit 1, Unit 2, and we want Unit 3, Origin of Microbiological Contamination of Foodstuff, with the presentation here. So let me open it. And full screen. Yes, this is it. Lysiane,
Yes.
the floor is yours.
Thank you, Wilfried, for the presentation. So I'm Lysiane Omover, project manager in ARL, and today I will present you 2 units, Unit 3, and then just after that, the Unit 4, and translated now in 3 languages. So for this first presentation, Unit 3, we are talking about the origin of contamination of foodstuff. Next slide, please. Maybe Wilfried, I can try to, or not, to change the slide. Not sure.
Can you try?
No, it doesn't work. I will tell you when we need to change. Okay, thank you. So the microorganisms that are found in food can form a variety of sources. It can be present in the raw materials and or ingredients. Contamination can be linked to the handling or processing of the raw materials. Microorganisms can be found in the factory environment, such as in processing water, in machine surfaces, in stencil, personal, or earth. For these two sources, it's mainly pathogenic bacteria and small-age flora that can be found, or hygiene indicators. Another source of contamination are the microorganisms that are voluntarily added, such as in a technological process with lactic starter or ripening flora. And in this case, it beneficial flora such as technological or preservative. So microorganism contamination can come from a variety of sources. First, they can be from the raw materials. It's microbial ecosystem naturally present in flora or plant or animals, and it can contaminate the environment with different origin. First, microorganism can be brought by the water with waterborne microorganisms from the soil, for example, Pseudomonas, Bacillus, Micrococcus. It can be also contamination from fecal matter, with example of Enterobacteriaceae or such sometimes pathogenics for humans, with Salmonella or Shigella, for example. You can also, air is the main source of molds, with example Aspergillus or Penicillium. And sometimes bacteria can be brought by the air with Micrococcus or spore-forming bacteria. And the third sources of raw materials is the soil that can bring telluric microorganisms or microorganisms carried by irrigation, water, wind, and insects. In the processing environment, there is 4 origins of contamination. Microorganisms can come from raw materials or ingredients which are a source of dissemination in the factory environment. It can be also from production workshop with contamination of floor, walls, or air contamination. Microorganisms can come from materials which are sources of contamination, for example, with equipment, belts, conveyor, or utensil. And then the contamination by personnel can be also another source of contamination, with hands, the use of gloves, apron, or aerosols. Here in this table, we give you some example of origin of pathogenic bacteria. In this table, you have in the first column the origin of microbial contamination, for example, fecal contamination from animal or human's digestive tract or excrement. And the pathogenic bacteria present in these fecal products are mainly Salmonella, Clostridium, Campylobacter from poultry, Yersinia from pigs, or Vibrio from fish or shellfish products. And Escherichia coli can be also found in fecal contamination. For environmental contamination in water, air, soil, dust, or plant surfaces, Listeria can be found, Bacillus cereus too, and Salmonella. And some Clostridium can be found too, Clostridium botulinum or Clostridium perfringens. And Staphylococcus aureus is mainly found when there is a human contamination. It's a bacteria that is present in saliva, in nose, or in skin infection. Here in this table, we give you some example of microorganisms involved in spoilage. You have a list of some microorganisms, such as Pseudomonas, and we listed the main routes of food contamination. For Pseudomonas is mainly found in milk, in plant, or in meat, and it can be also found in processed waters, surfaces, and specifically in biofilms. Enterobacteriaceae is also found in various raw materials, in milk, plant, meat, or fish. And these bacteria are mainly bring from staphygen or surfaces. The same thing, lactic acid bacteria are present in various raw materials, and in environment, they are mainly found in surfaces. For spore-forming bacteria, they are also present in various raw material and also in dry ingredients, and found also in surfaces. And for yeast and molds, they are mainly present in plants, fruit, cereals, and they are found in air, surface, flow, and walls. So to conclude on this unit, to preserve the safety and the microbiological quality of food, it must be important to identify the origin of contamination and to have knowledge of the microbial ecosystem of raw materials, and to do some samples and analysis of the manufacturing environment. It's also important to implement control measures to prevent, to eliminate, or to reduce the presence of pathogenic or spoilage flora, with good hygiene practices applied to control the contamination linked to the manufacturing environment. Yes, it's okay. Sorry. And then you can find some control level to avoid or limiting contamination. For example, to control staphygen, you can avoid or limit contamination caused by handling. With a flow management or air analysis, you can avoid cross-contamination too. Another control lever is to manage the pests, and it's also a good way to avoid external sources of contamination. You can also apply, to some cleaning and disinfection application to eliminate contamination and to avoid biofilm formation. And then you have to put an hygienic design of equipment to ensuring the cleanability of equipment and preventing the formation of biofilm. So thank you. And if you need more information, you can go to the platform and to follow the other units and other levels.
So now we will switch to the Unit 4. We will show the presentation of the Unit 4 conditions for the proliferation of microorganisms and control measures. We will do the same here. All right.
Yes, thank you. So here is the Unit 4, also from the basic level and translated in 4 languages. So as we previously described, there is 3 categories of microorganisms, different microorganisms. Some good microorganisms that are technological flora, bioprotective or biopreservation flora that can be used to combat pathogenic or spoilage flora. For example, Saccharomyces used in bread, Penicillium roqueforti used in cheese, or Geotrichum or Brevibacterium linens used for cheese ripening. Another category are microorganisms that are bad. It's mainly spoilage flora that can degrade product quality. It can be also hygiene indicators that can indicate the presence of pathogenic bacteria. And for example, you can follow coliform, Pseudomonas, or heterofermentative lactic bacteria. And the third category is the pathogenic microorganism that represent an important microbiological risk in food products. For example, Listeria monocytogenes or Salmonella. Different microorganism, but it can be a good or a bad microorganism, like a living thing with specific needs in order to grow. So microorganisms need different things to grow. First, they need to eat. They need a source of energy. It can be nitrogen, carbon. They need water and some nutriment. Microorganisms have a specific metabolic way to breathe. Some bacteria need oxygen to grow. For example, moods on the surface of the products or Pseudomonas. These microorganisms are named strict aerobes. Some other microorganisms hate oxygen, such as Clostridium botulinum, and they are named strict anaerobes. And others are indifferent from the oxygen. They need or they don't need the oxygen, such as Salmonella or Listeria, and they are named facultative anaerobes. Other factors will also come into play and have an impact on their development, mainly environmental factors. So the microorganisms have also their limits. Their growth depends on a number of factors, such as the temperature, the pH, or the water activity. Each species is characterized by cardinal growth value. There are some minimum growth value for temperature, for pH, and for water activity. Each microorganism have a maximum growth values and also an optimum growth value for temperature, pH, and water activity. For example, for temperature, there is different categories of microorganisms according to their capability of growth in various temperature conditions. First, there are some psychotrophs. They can grow at temperature below 8 degrees. Mesophile microorganisms can only develop between 10 and 45 degrees, and thermophile microorganisms that can develop between 15 and 17 degrees. pH is also an environmental factor that can decide the growth or not of microorganisms. Some microorganisms cannot develop below pH 4.5. And the third factor is water activity. Bacteria cannot grow below water activity under 0.92, but some species tolerate lower values. And for example, yeast and mold can grow below a water activity of 0.90. Here we give you some example of limiting factor for each microorganism. For example, Listeria monocytogenes is able to grow at 6 degrees and at pH at 4.4. And E. coli, for example, can grow at low temperature but is unable to grow with a low pH level. Clostridium perfringens cannot grow at 6 degrees and cannot grow at pH 4.4. So, however, food is a complex environment. There is not only temperature, water, and pH activity. There is some other intrinsic factor in the food, such as the presence of organic acid, lactic acid bacteria, or acetic acid, for example. The presence of ingredients can also influence the growth of microorganisms, the type and the level of preservative. The presence of microflora can also influence the growth of pathogenic or spoilage flora, and the product structure and composition can manage to the growth of microorganisms. So there is also other factors, temperature we'll talk previously, but the type of packaging can also have an influence, and the type of atmosphere used. There is some different condition with air or vacuum or modified atmosphere. So is it important to considering the manufacturing processes and to consider to be conscious that every foodstuff is different. So to control, there is some control measure to prevent the growth of microorganisms. And an EC regulation stipulates that no food shall be placed on the market if it considers to be dangerous. It can be injurious to health or unfit for consumption. To achieve this, the food chain operator must put in place and validate control measures to prevent, eliminate, or reduce the presence of pathogenic flora. Okay. So there is different levels that can be managed to control the growth of microorganisms. It can be to manage the hygiene during the food processing. It can be the processes too. You can manage on the formulation with the use of preservatives, the use of ingredients, or the use of technological flora. And then you can manage the shelf life. For hygiene, for example, it's important to identify and to prevent possible sources of contamination. There is 5 mainly sources of contamination. As we showed previously, it can be materials with raw materials or ingredients. It can be the manufacturing workshop, the environment organization. A source of contamination, it can be the method, the process used for the food product, manufacturing process, the recipe. Contamination can come from machine with utensils, the use of equipment, and also from the staff. And it's important also to put in place cleaning and disinfection procedure to eliminate contamination and to avoid the formation of biofilms that protect microorganisms. Here we have just put a focus on cleaning and disinfection. So contamination of manufacturing can be managed by cleaning. So cleaning is the removal of dirt, organic matter, and mineral that support the adhesion of microorganisms to surfaces and the nutrients that allows them to develop. And the other technique is the disinfection. In that way, to eliminate pathogenic or spoilage microorganisms that may contaminate foodstuff and prevent their proliferation and the formation of biofilm. So cleaning operation must be carried out before disinfection, regularly at a frequency appropriate to the production cycles, with products authorized by the regulation without leaving chemical residues on food contact surfaces. Another way to manage the microbial growth is to work on formulation. For example, by reducing the pH with producing a more acidic product that can limit the growth of microorganisms, or to reduce the water activity. And it's two ways to slow down or to inhibit microbial growth. It's also possible to use certain additive or preservative, inhibit or slow down the development of flora, such as organic acid, the use of nitrates, sulfate, or sorbate. Nevertheless, additives are subject to authorization and labeling rules. It's also possible to act on several factors at the same time, the use of ingredients and the reducing of pH, for example, to limit the bacterial growth. For example, for Listeria monocytogenes, this pathogenic bacteria is not able to develop in the product if the water activity is below 0.92, or if pH is below 4.5, or a combination of these two factors, water activity below 0.94 and pH below 5. In these three conditions, Listeria cannot grow in the product. The third way to manage the microbial growth is to manage the processes. There are many processes that can be used to sanitize foods or inhibit the growth of microorganisms. For example, you have some technical step that can limit the growth of microorganisms, such as salting, smoking, drying, or fermentation. Refrigeration and freezing can also limit the growth of microorganisms. And then final step is packaging and the use of protective atmosphere. There are some other technological steps in order to reduce the microbial loads, such as cooking, some pasteurization or ionization step, or the use of new technologies such as high pressure, pulse light, or cold plasma. And finally, it's another way to manage the microbial growth is to work on the shelf life of the products. So the shelf life of food products correspond to the period during which a product meets the specification of safety, food does not cause damage, and food is acceptable organical and nutritional properties under reasonably condition of storage and use, including by the consumer. Shelf life of product must be validated and verified in compliance with microbiological criteria during all the shelf life. And if safety is not guaranteed during the shelf life, it must be better to reduce it. So to conclude on this presentation, microorganisms have a great capacity for resistance, survival, and adaptation. Some microorganisms are resistant to it, for example, spore-forming bacteria. and some microorganisms can develop a NEAT resistance, such as Salmonella. There is also different microorganisms that can develop in other conditions. For example, in low water content, osmophilic yeast can develop. In acid conditions, some acidophilic bacteria can also grow. For example, Alicyclobacillus in beverage. And the cold change encourages the emergence of psychotrophic flora and certain microbiological hazards, such as Listeria monocytogenes. And to fight these various microorganisms present in food, it's often necessary to use a combination of the different control measures that we shown before, or with barrier technology. So thank you for your attention. And if you have any question, please don't hesitate to put it in the chat. And you can also find more detail and more information in the other level, at intermediate or advanced level. Thank you.
Thank you, Lisiane. Now we are going to switch to the other level. So we are going back in the same module, but we are going to the intermediate level. In this intermediate level, you have the general presentation of the characteristics or details of this, what you can find in this intermediate level. Then you have an initial quiz as usual. You have Unit 1, which is not our topic today. And then you have Unit 2, how to prevent and handle process deviations. So here I'm going to give the floor to Mrs. Mariam Zanzan from IPV in Portugal.
Thank you. So I will try to share my screen.
Okay, can you? Okay. So, hi, Mariam. Yeah, we can see you now. So, yeah, please, if you can, share your screen and you can handle it from your side.
Can you see my screen?
Yes, it's okay.
Okay. So, good morning, everyone. First of all,
yeah, if you could try to put it full screen, because we can still see your. We don't see the screen at the bottom. It might be this icon by plus 70% pressed. Then there is this symbol to enlarge on the gray line. Up. Yeah, sorry.
I'm trying to find it.
Yeah, on top of the logos, you have this dark gray line, and you have the page, the zoom 70%. Then you have this the other one. No, yes, this one.
This one? No.
Yes, no, but yes, but if you could continue to put in the right way, yeah. Then could you please try again the other one? On the yeah, that was good. Yes, please. Yes, this is perfect. Then we can see all.
So it's okay now?
Yes.
Okay. So good morning, everyone. Thank you for joining us on this webinar. So today's session, we will explore how to prevent and handle process deviations. So this presentation is led by our team researchers, Professor Ursula González-Barón and me, Mariam Zanzan, and also Professor Vasco Cadaves from Polytechnic Institute of Bragança. So preventing and handling process deviation is fundamental, as we know, because it can ensure the quality and the food safety of the product. And any deviations or unexpected variations during the production can lead to critical issues if not properly managed, of course. So let's focus on what we will learn during this presentation. So you will understand how to identify, prevent, and correct process deviations in order to maintain a high standard of quality and safety, and also the different actionable strategies to anticipate or to prevent any irregularities earlier. In addition, we will learn different steps for reducing microbial contamination. So as a content, we will start with the introduction to set the context, then different monitoring techniques for process deviations, including visual inspections, microbial testing, environmental monitoring. And after that, we will move to different strategies for controlling deviations, from preventing and handling to corrective actions. And we will talk briefly about developing a contamination control plan using hazard analysis and critical control point system. And finally, a conclusion. So, controlling process deviations is crucial for maintaining the integrity of manufacturing process, ensuring product quality, and safeguarding consumer safety. So let's think about it as a routine health check for food production. And as we know, a checkup is vital for our health. The same, controlling process deviation, ensure a clean and safe environment to prevent the contamination. So as illustrated here, we have 3-step cycles. We start with measuring the actual performance. So continuously assessing the process in order to detect any irregularities or anything that can be critical for our process. After that, we have comparing actual performance against standards, which means to evaluate the current process if it's aligned with the quality and the safety of the safety standard. And if there is any problem, we have to immediately act with corrective actions, which is the step 3, taking managerial action. So as I said before, if the process deviations is not properly managed, it can lead to significant challenges, including product recalls, regulatory non-compliance, and the most important is the loss of consumer confidence. So for monitoring techniques for process deviation, visual inspection is one of the simplest and effective methods, which involve workers or staff directly in order to observe the process, equipment, and the work environment to identify any anomalies or any deviation in food being processed or equipment, and deviation from standard operating procedure or sign of contamination. So here we see that the workers try to detect any irregularities from machinery or from the key areas during the production to anticipate any problem. And another method is the microbial testing, which means to take samples from different areas or different points in the process and environment, and then try to analyze them to identify and quantify the specific microorganism. So here as examples, we have PCR, which is polymerase chain reaction, where DNA component is amplified and trying to detect the presence of microorganisms and also to quantify them. using this method. Also, we have a culture technique, which involves to collect samples and incubate them in appropriate medium and appropriate temperature and time in order to see if there is any growth or no growth of microorganism. And those methods are crucial for validating the safety of product and the cleanness of the environment, of course. So when we talk about environment, so it means monitoring the physical, chemical, and biological factors of the production environment. And this is essential for ensuring the quality and the safety of the product. And there is different key factors, can include temperature, humidity, air quality, particulate levels. So as example, if we have the level of temperature or humidity that is below the requirement, it will increase the microbial contaminations during the process. Here, as examples, we have displayed tests for air in order to detect the microbial contamination of environment where there is the production. Also, we have hygrometers, thermometers to measure the humidity and also the temperature. So let's move to the strategies for controlling deviations. One of those strategies is preventing deviations. So preventive measures are fundamental to controlling deviations in the manufacturing process. So by focusing on prevention, the food industry can maintain a high quality standard, ensure regularity requirements, and protect consumer safety. As example of preventing deviation, we can use the good manufacturing practice, which is a set of guidelines and regulations that is established to ensure the production and manufacturing of safe and high quality product. So it provides control and monitoring of manufacturing process, facilities, and equipment. So by implementing the good manufacturing practice, the companies can minimize risk associated with production deviations, ensuring that process align with the safety and quality requirements. So as examples of good manufacturing practices, we have sanitation and hygiene control, so which means to provide a cleaning protocols where we describe, for example, the area or the equipment, giving more details about the method of cleaning used, the frequency, which means is it one per day or twice per day or depend of the production. Also, the person who is responsible of this cleaning schedule. And this is for the whole month, of course. And another example is the equipment maintenance, where we try to track the equipment maintenance, given the date, the time, the code of the equipment, the person who did the check, and also the company name. Another example is the personal training. So the registration of personal training highlights the importance of continuous training for the workers or for the staff. So it's important in order to ensure that the employees know about their role and their responsibilities in maintaining product integrity. Also, we have staff hygiene cleanliness check, and this for monitor hygiene practices, assessing compliance with health standard to prevent contamination, and it focuses on health, behavior, and the safety of the workers. Which means to check whether workers are wearing gloves, mask, clean uniform, also to verify that the employees wash their hands regularly or not, etc. The same for the control of storage conditions. So we monitor the storage environment for temperatures, and the product type is also crucial for preventing the spoilage. So another method for preventing deviation is root cause analysis. So a root cause analysis is to identify the primary cause of a problem, so that problem can be stopped from happening in the first place. And among those methods for root cause analysis, as illustrated in the diagram, we have the method of what we called 5M. 5M, which means man, method, material, machine, measurement. So for example, for the first M, which is man, it's the human factor. So such as if there is a lack of training, improper practices. Also for the machine, which is the equipment. So if there is any malfunction or improper maintenance, it can lead to cause deviations. We have the third M, which is the method, and this focus on the process and the procedures used in place. So any poor definition of procedure can result to different problems, of course. We have also material. So we examine the raw material used in the production. So if there is any contamination of ingredient, it can directly impact the final product. And finally, measurement. Inadequate measurement tool or method used can lead to different deviation. So applying this 5M framework, we can identify the root causes leading to more effective corrective actions and improved process. So as a root cause analysis, we have, as we said, 5M, and we have other methods such as 5 whys, which means that asking why 5 times in succession in order to find the root cause of the problem. Let's take an example of in dairy plant. For example, we have a problem of milk spoilage. So we can start with the first question, why, which is why did the milk spoil, for example. As an answer, we can say that maybe the temperature in the storage tank was too high. So the next question, it will be why the temperature is too high. So we can say that the cooling system failed. So the other question will be why the cooling system failed. Maybe because the compressor was not functioning well. So the fourth question will be why the compressor not function properly. So maybe it had not been maintained. So the last question will be why it not been maintained. And the answer, it will be because there was no scheduled maintenance, for example, which means that we need a maintenance schedule for the cooling system. So here we can identify the root causes of this milk spoilage, for example. The second strategy for controlling deviation is handling deviation, which means corrective actions. So this corrective actions is not only it's not only addressed to when we have problem, but also to prevent them from acquiring. And to do that, we have different method. We can use the hazard analysis and critical control plan, that point plan that address food safety hazard associated with the microbial contamination, or we can use alternative documented procedure that can ensure the safety of final product. And the detection during the process deviation can be happen in process, which means in a real time, or can be happen after process, which record the review. So in the case that it's detected during the process, and in the case that we don't have any alternative document or HACCP plan, in the case we have 3 options. So we have to immediately reprocess product using a full process schedule. As example, still in the dairy plant process, if we notice that the temperature of pasteurizer has dropped below the level required, so the action that we have to take is to stop the process line and reprocess the milk using a full pasteurization schedule in order to ensure milk reach the requirement safety standard. Or we can use an alternative process schedule that is approved by a quality manager chef, or we can handle the process and evaluated by a quality manager. In the case that handling processing is identified in record review, so the processors must maintain a complete record regarding the handling of each process, including appropriate processing and production record, a full description of any corrective action taken, the procedures and the results of process deviation evaluations, and the disposition of affected product. So let's move to the process deviation option that we can have. The first one is to rework. If we have any deviation, we can rework the product, which means that we can open the container and try to rework the product back into another batch in order to be used, or we can use it for the production of another process. So to be, instead of being as a raw material for the process, it can be as an ingredient in another process. But the problem of this rework is that it can change the product properties and can affect the heat penetration. Another choice is the evaluation. So to establish may hold product and submit the information to safety specialized engineer for evaluation and review. And if we cannot do any of those choices, the last choices that we have is to destroy the product instead of use it. So here, the implementations of corrective actions that should be taken to fix the cause of an identified deviation or non-conformity. So it can include to fix the cause of an identified deviation or a non-conformity. It can be include equipment repair or replacement, or change in material handling procedure. As we can see here, first of all, we define the root cause. After that, we implement the solution. Then we verify the solution workers, and we try finally to resource other solutions. So we can say it's like the control cycle, what we called PDCA. So P for plan, D for doing, and check to verify the action, the corrective action or the solution, and finally act to improve more this solution. So here it's as a checklist of different implementation of corrective actions. As we said, we start by identify the deviation to document the occurrence deviation. After that, the root cause analysis. to conduct an investigation of the cause of this unexpected variation. Then corrective action plans, so to detail given different specific measures of this corrective action. And then we execute the corrective action. After that, we do a verification. And finally, documentation, which means to maintain comprehensive record of the contamination issue, the investigation finding, the corrective action taken, and the result of verification effort. So here, I want to focus on training and communication. So informing and training staff about deviations that happen or the cause of deviation and the corrective action taken and any change to procedure or protocol is something important to ensure also that all relevant persons are aware of the changes and understand their role in preventing a future deviation. So employing or the workers' training and communication, it's essential because the employees should be aware of any change of any process or any procedure or any update about the procedure. So any update about the procedure should be right at the top of the procedure document with the version. So if there is any change, we have to put there version 1 or version 2 and the date of the update. It's important. So like that, everyone can help and can stay aligned and understand which version of procedure is currently used. So for the last slide is about control plan using hazard analysis and critical control point system. So this plan is designed to identify and address food safety hazard associated with the microbial contamination through the production process. So I will stop here, and if you want more information about hazard analysis and critical control point, there is other courses on the platform with more details. So thank you very much.
Thank you, Mariam, for this presentation. So we are a bit ahead of the schedule. So there's just one comment on the chat. Maybe you can answer, Mariam. I'm going to read the question or comment from Magda. During your presentation, she wrote that this. So it's about rework and about the batch number. So this the comment is that this would depend on the type of product. Rework does not necessarily mean changing the batch number. Do you have any answer to bring to that comment, or?
So for the rework, we said that we can change the batch. We can use another batch to fix the deviation that we have in order to not lose our product, and also to do different evaluations of the final product. And if we have any problem in this, we will see, it depends on the activity of the company. We can use this product for another products, of course.
So it's not compulsory to change the batch number. It depends also on how the company works with that. All right. So this is it for this control of microbial hazard modules. So we will have a coffee break now for 15 minutes. So yeah, Magda added that it depends on the product. Yeah, this is it. Magda, if you have any additional comment or question, feel free to write in the chat. And if not, for those who have not read on the chat, there is the possibility now for you to access to the quiz, to the webinar quiz. So you have to go to the platform, to the ISEKI e-learning platform, to connect to the microbial shelf life module in the basic level, and here you will find the webinar quiz. You can start now, and you have until 10:45, until the end of the coffee break, to do it. And then we will continue with the presentation of the other module about. So this is the risk analysis module, and then we will talk about the results of the quiz before the conclusion. So you can still have 5 minutes. So this is the webinar quiz. Webinar quiz. It's yeah, I'm going to write in the chat.
It's located in the microbial shelf life module, basic level, and then you will see the modules in English, French, Portuguese, and Spanish. And the first one, you have the quiz of the webinar. And now it should work. We apologize for this, but now it should work. And I see there are some people which are already answering the quiz, so it's working.
So I can show some. Okay, this is Ruiz. Yes, I'm going to share my screen again to show. But I might not have the same presentation on the screen, but still, it's could be a good way to show to people. So when you connect to the overview of the e-SafeFood project, you have the microbial shelf life module. You connect to the basic level, and here you have the quiz webinar. And you have the questions that will appear, and you can click here. So it's a multiple choice. You can also have several answers for one question, and then you go to next page, and you have 7 questions to answer.
Yes, and you are going to be asked for the enrollment key.
Okay.
And this is e-safe for all. It's written in the chat. Because this was the reason why it was not working, because the enrollment key was not set up. So yeah, your screen is a bit different, Wilfried, because you have manager, right? So it's easy to be found, yeah.
So last time for everyone. So under the e-SafeFood project, microbial shelf life module, basic level. Then you have the key, the enrollment key, as Luminita said, is e-safe for all, as written here. It's also on the chat, and then you can access to the webinar, to the quiz. Yeah, all right. With the question 1 and so. So I hope it's going to work for everyone. Let us know. So you still have. It's now 10:30. We still have until 10:45 here. The end of the coffee break will be in 15 minutes. So you still have 15 minutes to answer the 7 questions. It's going to be enough time to do it. And then, or we can still also close the quiz at maybe. Luminita, what do you think?
Yes, yeah.
If some people have some technical issues.
Yes, we can keep it, yeah.
Until 11, and yeah, then we'll find the results
yes, at the end.
after the presentations of the risk analysis. So let's have coffee now, and see you in 15 minutes.
Yes, it's okay. So good morning, everyone, and thank you for being here today. So I'm Benjamin Duquet. I'm a project manager in microbiology at ACTIA, and I'm going to introduce the basics of the risk analysis and the risk assessment of foodborne pathogens that is available on the risk analysis module. So as a reminder, and as you know, food industry operators are responsible of the safety of the products they put on the market, and they must respect microbiological criteria set, for instance, in the European regulation from 2073. And to comply with these criteria, but also with other requirements, they follow health control plan or sanitary control plan, among which control measures are identified. And all of this is integrated into the company HACCP plan. So in the food industry, control measures must not only be identified, but they need also to be validated. And companies have to implement monitoring procedures to verify that these measures are effective. And this verification can be based on experimental measurements with challenge tests, for example, of the use of predictive microbiology that you can find in the microbiome shelf life module if you want to know more about this. And sometimes risk analysis goes beyond traditional criteria by using quantitative microbiological risk assessments, which involves modeling and numerical simulation to estimate consumer health risks following an exposure to microbial hazards present in the food. So now, what is concretely the quantitative risk analysis? So risk analysis consists of three main components: risk assessment, risk management, and risk communication. And briefly, risk assessment is a science-based process composed of several steps that we will discuss later, while risk management involves evaluating policy options to protect consumer health. And finally, risk communications ensures that stakeholders, including the public, industry, and authorities, can exchange information effectively. You can go on the next slide, please. Thank you. So, risk analysis is used to develop an estimate of the risks to human health, to identify and implement appropriate measures to control the risks. And of course, it contributes to better food safety outcomes and improvements in public health. So the first element we are going to address is the risk management. So risk management follows a four-step process. The preliminary risk management activities, the identification and selection of risk management options, the implementation of risk management decision, and monitoring and review. And it is an iterative process where all elements are linked together and can interact between them. You can go after. Yeah, thank you. So the first step of the risk management is the preliminary risk management activities. Basically, the idea is to identify food safety issues and to gather scientific information into a risk profile. For example, salmonella in meats. And the second step of the risk management is to identify and evaluate the possible options for managing the risk. For example, the risk management goal is to reduce the contamination of salmonella. And in this process, I have a heat treatment. So one option will be to increase the temperature of the treatments, or maybe the durations, or other steps in the process. The third is to ensure that the industry adheres to regulatory standards and monitor the effectiveness of safety programs like the HACCP. And as you remember, and as you know, the industry has the primary responsibility. And lastly, we need to determine if the measures that were implemented are achieving the risk management goals set established in the first step. So in risk management, I said previously that the company and the governments had to define some risk objective, and they have to monitor the implementations of measures. So in this context, new metrics such as the appropriate level of protection, so ALOP, and the food safety objective, FSO, can be used. The LAOP is a national public health objective and generally expressed as tolerable number of illnesses per inhabitant per year for a given hazard and food pairing. This metric must be defined by the member states and justifies the management measures put in place on the basis of a scientific risk assessment. And LOP is not directly applicable at industrial level because it's generally linked to a country. The second matrix, the FSO, is expressed as a frequency or that depends a maximum concentration of a microbiological hazards, but it could be also chemical. But in our case, it's microbiological hazard present in the food at the time of consumption, which enables or contributes to achieving the LAOP. And we'll have an example later of a link of the two metrics and other metrics. If the FSO is a threshold not to be exceeded at the time of consumption, and it's important, it's at the time of consumption, it is however necessary to define sometimes target threshold upstream, and therefore the company, and this is the case of the performance objective, so the PO. And a PO corresponds to a maximum frequency or concentration of hazards in a food at a specified step in the food chain. So this is the difference between the PO and the FSO. And for example, from my previous heat treatment of salmonella, for example, my maximal concentration of salmonella after this step should not exceed, for example, 1 CFU per 100 grams. Another metric that can be used is the performance criteria, so the PC. This is the effect required of one or more control measures to meet the PO. For example, still with my heat treatment of salmonella, if my contamination before the heat treatment is 100 CFU per gram and my PO after treatment is 1 CFU per 100 gram, per 100 gram, my PC will be 4 log because I want to reduce my contamination of 4 logs. And then the two last are the process criteria and the product criteria. So there are control parameters that can be applied to achieve a PC. So the product criteria is linked to product. It's in the name. So we can act on the pH, on the water activity, for example, and on for process criteria. It's more related to your process. So you can act in the treatments, the durations of the treatments, the temperature of the treatments, and so on. So this is just an example to understand how all metrics are related. So for this example, we will be interested in Listeria monocytogenes. So we can follow the other process from farm to fork. And for this pathogen, the LLP is less than 1 case of listeriosis per people per year. So to be compliant with the LLP, an FSO was set, and company can also set a PO if necessary. And for Listeria monocytogenes, the FSO is prior to 100 CFU per gram at the consumption time, and it's especially true for ready-to-eat products. And to achieve this FSO, the PO at the manufacturer release is inferior to 10 CFU per grams. And because the food business operator, through a challenge test, know that Listeria can grow in its products, but not enough to exceed 100 CFU per gram. And just a small aside, if a producer cannot justify that the criterion of 100 CFU per gram will be not respected at the end of the shelf life, in this case, the PO becomes absence in 25 grams. I answer for a question. 100 CFU per gram is for Listeria monocytogenes. And during the process of transformation, the FBO has set PC inferior of 1 log of growth during the food preparation. And to achieve this PC, a product and a process criteria was set. And in this case, the pH of the product have to be equal to 5. And the temperature of the plant has to be inferior to 8 degrees to limit the growth of bacteria. You can change the slide, please. Yeah, thank you. The next, please. Yes, thank you. So in practice and at the operational level, the considerations of the different metrics can be summarized according to the following equations. H0 minus the sum of the R plus the sum of the increases less than or equal to PO or FSO. So H0 is the initial contamination concentration usually at the beginning of the process. The sum of R corresponds to the process steps that can lead to a decrease in the concentrations of microorganisms, and conversely, I, the process steps where growth or a recontamination can occur. For instance, if the FSO is equal to minus 1.5 log CFU per gram and H0 equal to 2 log CFU per gram, the sum of reduction and increase should be equal to 3.5 log. Just keep in mind that to achieve the same objective or the same FSO, several options are possible to control all the process. For example, the FBO can reduce the initial contamination or it can also increase cooking parameters to reduce more effectively the population, or it can also decide to add preservatives or reduce the shelf life to limit the growth. So if you remember, risk analysis includes 3 elements. So we have seen risk management, and now we will focus on risk assessment. So this approach uses modeling and numerical simulation to estimate the risk of adverse effects, either illness, DALY. DALY, it's a metric, so it's for disability adjusted life year, and basically is the number of years of healthy life lost due to disability or even death for the consumer. Following exposure to a microbial hazard present in the food. And it takes into account the entire life cycle of a product, so from farm to fork, and the characterization of risk typically contains both qualitative and quantitative information, and is associated with a certain degree of scientific uncertainty. And basically, the uncertainty is represented by the confidence interval. When quantitative data are used, it quantifies usually the impact of a manufacturing process or control measure or raw material contamination on consumer risk. And risk is often expressed as a probability. And we can also calculate the percentage of risk reduction achieved by the application of a control measure. For example, if the storage temperature is changed, is it then possible to estimate the impact of change on the risk? So the risk assessment is composed of 4 steps. So the first, identifications, the hazard characterization, the exposure assessments, and the risk characterization. And we will quickly go over these different stages. So the first step of risk assessment is the hazards identification. So as a reminder, a hazard is defined as a biological, chemical, or physical agent in a food that has the potential to cause an adverse health effect. So it's our case, it's more biological hazards. And in microbiological risk assessments, the microorganism is generally recognized as a pathogenic agent capable of causing disease in humans. And the hazard identification stage consists of evaluating the epidemiological or experimental data available to support the hypothesis that the food in question plays a role in the transmission of the hazard to humans and also the onset of disease in them. So this step is purely qualitative because the main idea is to gather available data from literature, for example, to conclude whether or not it's appropriate to perform a risk analysis. Here are some examples of information that can be useful, such as the role of food in the transmission of hazards, the pathology associated, and the adverse effects on humans, the frequency of contamination, and if the current food processing methods can eliminate the presence of the hazards. once all this work has been done and it has been deemed appropriate to use the quantitative risk assessments, it is possible to move to the next steps. So one of the next steps is the hazard characterization. This stage involves assessing the nature of the adverse health effects associated with the hazards. So it's always a combination of these two. And the main objective of this step is to establish the dose-response relationship. And in other words, and from what quantity ingested I can get sick. Unfortunately for us, the ingestion of pathogenic bacteria does not result in an infection or illness. Indeed, various factors will have an influence on the risk of having an illness, such as the multiplication capacity of the bacteria, the virulence also, bacteria, the matrix, and the host. Because every person is different, the immune system does not react the same way for everyone. So it has to be taken into account. Here you can see at the bottom, it's just an example of dose response model where we can see the probability of illness according to concentrations with its interval confidence. It's maybe a bit small, but just for instance, if we ingest 2 log of a bacteria, the probability of illness is 10%. You can go next, please. Thank you. So the next step, the other step after the hazard characterization is the exposure assessment. So in this step, the goal is to describe and quantify the exposure to a hazard. That means the estimates of a probable ingestion of the hazard via food. This step is very complex because many data is required. And to perform the exposure assessments, we need to estimate several things, such as the probability that the product consumed will be contaminated, because in fact, not all products put on the market will be contaminated, thankfully. The difficulty is also that this probability can vary a lot according to the origin of a product. For instance, some batches can be more contaminated than others. And also the changes over time in growth parameters, especially if the process is not well controlled. And pH or HW can vary greatly between batches. And the other elements are the concentration of the hazards in the contaminated foods, the frequency of consumption of food products, and the quantity of foods consumed that can vary from one individual to another. So this variability makes exposure assessments even more complex and difficult to use. And the last step of the risk assessment is the risk characterization. Basically, we'll take the data from the hazard characterization and exposure assessment, and we combine them to provide a quantitative estimate using calculation software. So the results of the risk estimate can be expressed as follows. Just an example. So we have 95% probability that the number of deaths linked to the consumption of food contaminated by the hazards under study will exceed 10 per year. And the variability of the expected number of cases reflects all the uncertainties surrounding the data used. So I was just talking about calculations software. So here are just some examples of software that can be used either for predictive microbiology or for risk assessment. So, but I won't go further about these softwares, but just for your information. And the last component of a risk analysis is the risk communication. The objective of this step is to inform and enhance risk assessments and risk management strategies. So it's also an integrative process, even if it's less known than the risk management and the risk assessment, but this step is a continuous and integral part of the risk analysis process. And all stakeholders must be involved from the outset. And communication is a two-way communication, including feedback, perceptions, and acceptance of risks. But it is also necessary, and it's recommended, to develop a strategy of communication early in the risk analysis process, and even before risk assessments. So to make communication clear and accessible, even for those with little mathematical or statistical training, it is important to use technical documents accompanied by simplified summaries. And in addition, numerical estimates need to be supplemented by qualitative information, highlighting assumptions, variations, and uncertainties. The aim is to be very clear. And every piece of information and data used must be explicitly described and with full transparency as to its source. And finally, the need for additional data to complete the exposure assessment must be clearly communicated. So to conclude this presentation and to sum up, here is a global overview of risk analysis with the three different components, so the risk assessment, the risk communication, and the risk management. And for example, the first thing is to ask the right questions, so which hazard, which population, and so on. Then to gather all the data available in order to perform the quantitative risk assessment. And for instance, this quantitative risk assessment can be used for risk assessment, also to quantify the impact of control measures. And these models can then be used, for example, as a decision-making tool. So here are just some references. Thank you for your attention.
Thank you very much, Benjamin. That was very interesting, comprehensive. Now we are going to present you the Unit 5. Is Vasco in here? If you can show up, Vasco, you should be able to share the presentation, or if you prefer, I can also share the Unit 5.
Good morning. I can share it. I don't know if you want to let me know what you want, but I can share it. Okay.
Okay. If you want, you can share.
Okay. Good. Let's see. So I need to find share screen. Okay.
Should have the options.
Yeah.
The option to share.
I have it here. Okay. You can see the presentation?
Yes, if you could put it full screen.
Very good. Okay, good. So it's kind of like this because I can control the slides. Okay, good morning. Yes. So I will present some examples of exposure and risk assessment models. that we developed under a project with the WHO. So the objectives of this lesson are the following. You will learn the type of information that we need to conduct a quantitative risk assessment model, the outputs of a model of a Q-area model, and the utility of these models to assess what-if scenarios. So what do you need this presentation? We have access to some dashboards that we developed, and of course you need R because you have also R package that you can use to conduct this to do these simulations of QRA model. Okay, the content. So we start with some definition, data, and common outputs, and then I will go to the examples of QRA models for Listeria monocytogenes. We have a package and the Shiny, so I will show you how to install, and then I will show you the frozen vegetables model structure and assess some scenarios. Let's start with the quantitative risk assessment, definition, and data requirements. So as you can see in this picture, when we develop a model like this, we can go from the production to the consumer. So we have a lot of all the stages along the production, transformation, and storing, for example. So we can model and we can use all the information from farm to fork, let's say. So a QRA model aims to estimate and describe the transmission of pathogenic microorganisms from foods, can be animal, can be vegetables, to humans. So we want to model this occurrence. So there are a variety of methodologies, tools, and models that you can find in public health, microbiology, molecular biology, epidemiology, and of course, we need also some knowledge about modeling, and there it comes engineering and mathematics, and in general, data science. The common feature of a model, of a QRA model, in this case, we follow a model approach. So we need to model specific parts of the production system. A model should represent let's say a stable phase of production. We can model the field production. We can model, for example, the slicing of a salmon or something. So we need to find common characteristics in order to be able to model these stages. There are two types of process: the microbial processes and food handling processes that can influence on this model approach. Of course, we need to take into account the randomness of the system of these kind of models. So these models are said stochastic models, and we need to know probability distributions for the parameters. We assume we attribute the distributions to these parameters of the models, and of course we need to know about variability or distributions of true heterogeneity and distributions of lack of knowledge that we call uncertainty. For example, variability. If you repeat a trial in the lab in two different days, we will have variability. But sometimes we have different results without knowing the source of variability. So when you know the source, we call variability or error, but there are some variation that we cannot explain, and this variation is called uncertainty. Okay, and the common features of these QRA models, if you take a look to this model approach, we can model microbial growth in activation, depending on the stage that we are. If you store the food at environmental temperature, the microorganism can grow. if you submit the food to some pasteurization, then we will observe inactivation. During food handling, we can do mixing, partitioning, and then we can talk about cross-contamination. Of course, we can also remove some parts of the food, and this removal can be a source of contamination, but we can also remove some parts that are contaminated, for example, with peeling. Okay, considering the stochastic approach, we attribute different distributions to the parameters. These distributions can be discrete, like Poisson or binomial, and can be continuous, like normal, uniform, or log normal. So we need to know, in order to attribute this kind of distributions, we need to know exactly which distribution will be better for a specific situation. Okay, so the data requirements, we need the data depending on the situation. If you want to model from farm to fork, we need all the information. If you want to model a specific part, so you need to collect data from this part, for example, for slicing. And of course, we start with the risk assessment question. Okay, so we have a question that you want to answer, and you need to collect data that is appropriate for this question. Then you can do this risk assessment approach. How you will model the process according to your risk assessment question, and of course you can identify the food pathways. So these food pathways can be divided in stages that can better represent all the specific type of data according to the situation that we are dealing. If we have growth, if we have inactivation, if we have cross-contamination, so we need to find the correct food production pathways. Okay, so if you think in the factors that we need to control or we need to take into consideration that can affect consumers' exposure to the hazard, you can see this general picture where you can have the general characteristics of the foodstuff are very important. So we can go collect data from industry data, from the literature. For example, we can know the pH of a sausage or the other activity of a sausage. Of course, we can go to industry and have data, but we can have also information from research papers, for example. And of course, we need to have the frequency of consumption of the foodstuff. So in this case, you need to have data from national consumption databases. There are some information about this. And if you don't have this kind of data, we can use what it's called expert knowledge elicitation. You need to know the prevalence and the levels of contamination. This is also important. So, are the food contaminated? What is the prevalence? What is the level of contamination? So we go to also to food contamination monitoring surveys, literature, and you can also use the PFAS database where we are storing prevalence or occurrence of microorganisms in different foods. Of course, we can do also expert elicitation. Considering the different stages and storage conditions, we can go also to literature, and if we don't have information, we can use also expert knowledge. Considering the pathogens kinetics during processing, distribution, we can find data also in the literature, in challenge testings, and of course in online modeling tools that there are several available. The outputs of these models usually are the exposure assessment, let's say prevalence of contaminated lots at the end of production, for example, mean concentration of contaminated lots at the end of production or at the end of processing, prevalence of contaminated servings, that this is connected with exposure from the consumers to the microorganisms, and of course the microbiological concentration in contaminated servings or in any serving, depending on how you express the results. Okay, and finally we can have what we call risk characterization. Taking these data of exposure assessment, then we can have the mean risk of infection or illness per lot, for example, risk of infection or illness per serving. So we can express the data in different ways and according to different situations, according to the interpretation that we want to give to the results. Considering the models for Listeria monocytogenes, we have a shiny application. This is this picture represents the shiny application that I'm talking about. We have 3 commodities: frozen vegetables, smoked fish, and RTE cantaloupe. And you can simulate different scenarios with this tool. So for the installation, you need to go to the GitHub repository. We have 2 repos about that you need to install for this work. One is about those response models, specifically for Listeria. So in this case, these dose response models are specific of Listeria monocytogenes, and you can see here that you have the code that you need to run in order to install these dose response models. After installing those response models, you can install also this QRALM package, and you have also the code here to install it. For example, the first one, sorry, those response models, the QRALM, you run this code, and after installing all this package, you can call the library QRALM, and if you run this code, run example, you will have access to the Shiny tool to do the simulations. So after run example, you will get this application exactly like this. The landing page is the about page where you have some description of the Shiny application, but then you can navigate in these tabs to simulate for frozen vegetables, smoked fish, and RTE cantaloupe. I will do some exemplifications only for frozen vegetables, but then you can use it for the others. So a small explanation of the models that are implemented in these tools. For no RTE frozen vegetables, you can assess the effects of high, low occurrence of Listeria monocytogenes in pre-blanch vegetables, incoming during the processing, effects of blanching and post-blanching contamination, and effects of consumers' food practices, such as no adequate defrosting or no cooking. Okay, so for example, the frozen vegetables are intended to be eaten cooked, but some people can take it can eat these vegetables without cooking, so this can be a problem. For RTE diced cantaloupe, you can assess the transfer of Listeria monocytogenes through contaminated soil and irrigation water, effects of contamination of rinds during harvesting, and subsequent rind brushing. So along the process, effect of storage of whole cantaloupe before processing. If you store, the Listeria can grow or can die, so you can model this. Effect of cross-contamination during processing, dicing. So for this ready to eat, the cantaloupe can be diced and stored. So if you dice, you can contaminate, and then the Listeria can grow. And of course, you can assess also the effectiveness of the cold chain from end processing to consumption. For smoked fish, you can assess the effects of high and low occurrence of Listeria monocytogenes in pre-fillet fish. Let's say if you have a fish with high contamination or low contamination, what will be the impact? Effect of cross-contamination during filleting, effect of contamination during brine injection or dry salting. These are 2 processes of preparing these smoked fish by brine injection or dry salting, so you can compare the 2 situations. And the effect of smoking, effectiveness of adding starter cultures, some interventions that can help us to control the pathogenic microorganisms and other preservatives, and of course we can model also the naturally occurring lactic acid bacteria and the cold chain. So these are the main applications that you can use with these models. So, for example, in these frozen vegetables, we divide this model in different stages, and we have 8 stages, in fact, from production, blanching, partitioning, then we have testing, portioning, defrosting, cooking, and we finalize with the risk calculation. So these are the main steps, but we can adapt other models if you need, or if you think necessary, or if you want to test different processing systems. Okay, but for these frozen vegetables, it was the stages that were considered relevant, but we can input or we can change or add or subtract some stages. So in the application, we have a chance to choose the stage where you want to do your interventions. In this case, production, blanching. You see, so you can change the select for each specific stage, and you can change the parameters in all the stages. Okay, this select stage can help you in navigating along the process. So these are the results that we can get in a simulation. So we have 2 types of outputs here. We have the prevalence on the left side, prevalence and mean counts on a lot basis. So we have a lot, we have information of a lot, and then on the right side we have information about the prevalence and counts on a unit basis. Okay, so a unit basis can be 100 grams, half a kilo, 1 kilogram, and we can define that, and then we have the contamination of the prevalence for a lot data, and we have for the units. You can see the prevalence of contaminated lots, the prevalence of contaminated units, and of course also the mean counts, in this case for between lot, what we call between lot. In this case, this is the between unit count. Okay, so we start with the production lots in this example, go to blanching, then we divide the bulk that are arriving from the production, and we do the partitioning. Then we portioning for at home level, we defrost and we cook or not. So these are the steps that you can see. At production lots, you can see, you can define the number of lots that you want to test, the size of lot, and the unit size that your bag is a bag of 500 grams or 1,000 grams, 250 grams. There are different situations. You can model that. So you need to have this is what we call 2-dimension Monte Carlo simulation. So we have a matrix with these dimensions. If you increase the dimension, the model will be a little bit slower. Okay, so we can also model the variability between lots. In this case, if you go to these beta alpha and beta parameters, these parameters are the alpha and beta parameters that define the beta distribution for the prevalence of contaminated lots. Let's say we developed a model where we can input variability between lots and within lots with this beta distribution. And then you have this on this left side, we have these three parameters. This is the proportion of between lot variance, and this is the mean log counts that you can find in the lot, and this is the standard deviation log counts. Okay, so you can change the between lot variability. Can be the lots can be completely different, or they can be exactly the same, no difference in the proportion of the variance of contamination, but you can input variation in this parameter at production level. Okay, you go to blanching. In the blanching is a simple set of parameters, the temperature of blanching and the time of blanching. So you can see what happens to the results if you change these two parameters. In this case, in blanching, we expect inactivation. So we use the log linear inactivation model, and the D and Z values are fixed and cannot be altered using this shining, because these are internal parameters. Okay, the recontamination, what we call partitioning, you can define the probability of cross-contamination. We can define the number of cells in the surface at starting. So let's say you are doing your you are filling your bags with 500 grams. We have the machine is contaminated. You can define if the machine is with low contamination or high contamination, and check what will happen in the results. And of course, we have also what we call dispersion factor of cells. If the cells are dispersed or aggregated, this can have an effect on the number of bags that will be contaminated. So you can model also these aspects. So this is in fact a recontamination stage where the bags can be recontaminated, and we are taking to call this recontamination. Okay, for testing, usually we can test, or we can do we can have a sampling strategy to test if our products are contaminated or not. So in this case, this testing stage was developed to check if implementing a testing or a sampling procedure can have impact on the risk. Okay, so you check all these parameters in the testing phase, and you can evaluate if the testing of a lot or different lots can impact in the risk. So this represents the Whitney lot testing for Listeria monocytogenes in food samples taken from a lot. So we are producing a lot. What happens if we test, and what happens if you not test? Okay, so you can define in this case the maximum number of samples except above M. You can put this to 0. The proportion of lots related to sampling must be specified. So you need to say, okay, I will test 10 lots or 1 lot or 2 lots, and say. And the sensitivity of the test can be set to a value lower than 1. In case the assay is their plating, enumeration, the sample weight must be indicated. So if you are enumerating, then you need to define the sample weight, okay? Because it's not the same to have 10 grams of testing or 100 grams. Okay, considering the portioning, this models the numbers of Listeria monocytogenes from a pack to a portion. Let's say we have a pack, we can remove a portion to cook, and we are simulating the Listeria monocytogenes that go in that portion. Okay, so this is a stage at home. So the serving size is the weight taken from a pack for consumption at home. This is the meaning of serving size. So you can decide. We have a bag of 500 grams. I will take 50 grams or 100 grams. So you define these. And of course, we can take also this dispersion of bacteria in the pack, because the dispersion can impact in the sampling or in the number of bacteria that you will get in a portion. Okay, considering the defrosting. The defrosting, we expect a fast defrosting. There is no growth, but if the frosting takes too long or at a high temperature, then we can have some growth of Listeria during this stage. Okay, so in this case we are modeling the growth of the Listeria using a log linear model without a lag phase. So we assume that there is no lag phase. And the parameters that you can select, the defrosting temperature, you can defrost different temperatures, the time that you are defrosting, and of course the maximum population density in the blanched vegetables, and the probability of defrosting. This probability of defrosting, let's say you can model a situation where 100% of the food are defrosted, and you can model also a situation where no defrosting is done and the vegetables are cooked immediately. Okay, so we arrive to cooking after defrosting, and of course we expect that during cooking the models we are modeling the depth of the Listeria during cooking according to, in this case, use the triangular distribution of the decimal reduction. Okay, so in this case cooking is always provoking the death of the Listeria monocytogenes. What you can model the probability of cooking. If everything is cooked, 1. If no cooking, you put 0. But sometimes you can model different situations according to these parameters. Okay, the minimum reduction, the maximum reduction, and the maximum Listeria log reduction during cooking. So you have these parameters that you can control during cooking. And we arrive to the risk, and after all the simulations, we compute the risk, and the risk is characterized according to different dose response models and population. If you come here, you can have the different models and different populations. Okay, so we have 4 models implemented: EFSA, WHO, and POYO. But and in these specific models, they developed situations for different populations, so you can check what will happen for a specific model and for a specific population. And this is the result. An example, we have in this case the mean risk per lot. You see the minimum, maximum, median, mean, and the percentiles. So that's how we characterize this kind of data. You can take a look at the median. It's 1.9 times 10 to raised to minus 17. So it's a very small number. It's a very small risk. And if you transform this in log 10, you will have minus 16. So it's a low risk. Okay, so now I will show you 4 what-if scenarios that you can develop and use it to check and to implement this strategy. We have some intervention at production of lots, at blanching, defrosting, and cooking, because these are the very important steps. At production, we can have very contaminated lots or low contaminated lots. So what if initial prevalence is double? If you have bad agar contamination, you change the beta to 1.5. At blanching, what if blanching is milder? Blanching time 0.8 minutes, and blanch temperature 75. So this is an important process. Defrosting. What if consumer defrost vegetables on the countertop overnight with a long time at environmental temperature? 4. What if the consumer wrongly used the non-ACTIA vegetables for smoothies? They don't cook it. They do prepare a juice, for example, with the vegetables, and they take it directly. So these are 4 steps that can be important. For the first scenario, we double the contamination at the production level. So the reference scenario, take a look to the median risk or mean risk, and in this scenario, if you can see the risk per lot increases 0.36. There is no big changes, in this case. A small increment in the risk. Okay, now if you have a blanching that is milder, what will happen? So a branching that can say is not correct or not normal in the scenario, reference scenario. And if you take a look to the mean, look, this number decreases 2 from mean, no, decreased 1 from 16 to 15, you know, from 16.7 to 15.2. So the risk increased 1.5 log 10, you know, so this is a high increase. So the branching is a very important step to control this Listeria monocytogenes in or the risk in the frozen vegetables. The third scenario, if you defrost overnight, so you expect growth, what happens to the risk? The mean scenario, the mean risk in the reference, and the mean risk in this scenario. If you can see, from minus 16 goes to minus 13, no? So 16.7 to 13.1. So there is a big increase in the risk, in mean risk per lot, you know? So we increase the risk with 3.7 log 10. So this intervention or this defrosting can be very, very problematic for this type of food. And the last what if scenario, if you don't if you don't cook, what will happen? Take a look from the mean, the reference scenario, we get increase in risk, you know. So the mean risk per log increase 3.2 log 10. So the previous defrosting and the cooking can have a big impact. And these are scenarios, independent scenarios. But if we join bad defrosting with a bad cooking, then the risk will explode. Okay, so as conclusions, the quantitative risk assessment models of pathogens are commonly based on a model approach, whereby the pathogen's fate is in a processing stage can follow any of the following processes: grow, inactivation, mixing, partitioning, cross-contamination, or removal. So you need to take into consideration all these processes. Using the WHO QRLM Shiny, it is possible to assess the effect of many processing stages, the effect of preventing cross-contamination and contamination events along the processing chain, the impact of different within lot testing schemes, the effectiveness of improved consumer practice related to handling and storage, and the effectiveness of intervention strategies. The QRLM Shiny has been developed as a tool for supporting decision-making by food safety authorities. So thank you very much. These are the sources that you can use to learn more and to understand the system. And I finish. Thank you.
Thank you very much, Vasco, for all these nice examples. We have questions relevant to your to the units you've just presented. So this is coming from Magda. She asked the following question. So the product which you create, the QRA model, is it frozen vegetables?
In this case, we developed the models for 3 commodities: for frozen vegetables, for RTA cantaloupe, and for smoked fish. And if I can show, let me just share the screen again. Let's see. I will try to entire screen. Okay, share. So this is the this is the application. You see. So the Shiny application is this one. You have for frozen vegetables here, okay, and you have the production stage or the risk, and you have for smoked fish and RTA cantaloupe. So in this case, we developed the application, the models for these commodities. Of course, some of the functions that we are using can be implemented for other commodities. Let's say grow listeria grow. We can model, but we need to adjust the parameters for a specific food, you know. So if you are working with meat, then the model needs to be adapted. The parameters should be adapted for the listeria grow in meat, because you are using the listeria grow in frozen vegetables or in smoked fish. I don't know if I answered the question or if I understand correctly the question.
We had also other questions from Magda. So can we change the commodities? I think the answer is yes.
Yeah, yes. In this case, we have only for 3 frozen vegetables, smoked fish, and RTA, but the not in the shiny, because the shiny is fixed. But with the air package, you can adapt the for different commodities. Yes, it is possible.
And can we change the stages?
Yes, of course. If you go to the air package, you can define your own stages. You can put more stages or remove some stages. In the shiny, I can do it because I can manage the shiny, but the stages are predefined. But with the R package, you can define your own stages along the process.
Okay. And one final question. I'm not sure about which software Magda mentions, but can this software be used to measure certain microorganisms on specific foods and packaging?
No, the software is just to simulate the risk. If you want to, I don't understand exactly the question, but you want to I don't understand exactly the question. If you want to know the number of pathogens, of the counts of pathogens in the food, I don't know. Maybe if the question is clarified, I can answer.
Yeah, Magda, could you try to clarify the question if it's not already clear for you? Maybe we can ask Vasco while we are still with this unit. If not, we also had some questions for the unit 1. I think previously in the chat. So we had a clarification requested for the ICMSF, and Valérie, one of the teacher who prepared also the content with us, answered that it's International Commission on Microbiological Specifications in Food. And we had a question from Magda. Again, Magda, thank you for your active participation. So this was maybe related to the unit presented by Benjamin. Is the intentional contamination included in the probability?
Usually, no.
Okay.
In the model, we use intended use of a product and intended, how to say, endogenous bacteria on the product.
Okay, thank you. Then we had sorry, I think I've missed one question from Ines. So the question is, are there concrete helpful examples for risk assessment for specific foods in the course material? So this is directed to all, I mean, both Benjamin and Vasco, but I think the answer is yes.
You have these examples, no? These examples are for concrete foods, and we use these frozen vegetables and smoked fish because there have been problems of health problems with these foods. So that's why we are developing these models to assess the risk, because we have some cases of contamination with listeria from these foods, you know. So these are real examples.
All right, thank you, Vasco. Another question just arriving from Nevijo. Vasco, so you presented risk estimations in CFU log 10. Can this be presented in relative risk, odds, or similar calculations?
Yes, you can. You just need to implement the calculations. Not a problem for that. Yeah, it's possible, but in this case, we adopt this mean risk per lot or mean risk per serving. That's usually how we present these kind of results.
Great, thank you, Vasco. Thank you for.
You're welcome.
Thank you to all participants for being active and for sending all these questions. It was very interesting. Now, if Luminita is ready, we can maybe show the results from the quiz.
Yes, I'm here. And do you see my screen?
Yes.
With the questions, yeah. So I will just shortly present the questions and the correct answers. With the mention that the platform is shuffling the questions and the answers so that if you do more attempts, you don't see the same order of the questions or the answers. So don't stick to the numbers and the letters that you see here. Just concentrate on the correct answers. So microorganisms in food have three possible origins, and they are that they pre-exist in the raw material naturally. They are added accidentally when food is handled during production, and they are presented on surfaces in contact with food. So those are the answers that you needed to tick. The next question, how should deviation in food manufacturing processes be addressed? And here you needed to say that maintaining food safety and quality. The next one, what does a control chart imply when data points are subsequently below the lower control limit? And here the correct answer is the last one, the process is improving and no further action is required, and or the control limit needs to be recalibrated. Question 4, what is the main advantage of creating a tracking and monitoring program? And here the correct answer is to identify the root cause of illness, minimize their impact, and prevent recurrence. Next question, what is the aim of the quantitative microbial risk assessment model? And here you needed to say that it estimates the risk of adverse effects for the consumer following exposure to a microbial hazard. For question 6, what is the prevalence of contaminating servings? And here the correct answer is the percentage of servings that are expected to have microbial contamination. And the last question, asking you in microbial risk assessment, why are challenge tests conducted? Needed to be answered with the aim is to assess the effects of processing and storage on microbial kinetics. So those were the correct answers we were waiting from you. And according to the statistic from the Moodle platform, we have an average grade of 8.43 out of 10. So the maximum was 10 and the average is 8.43, which I think is good. It's more than 8, which is the passing grade we have established for the, the quizzes also in the e-learning program. And here you can have a look at the grades. So we have here the majority of the respondents are between 840 and 9. So 20 of the participants have this average rate. Yeah, we had a total of 44 participants, but only 43 finished the quiz. And here it's the distribution of the grades. So I think this is a great result. And you have some knowledge, but go on the Moodle platform, follow the e-learning training, and you will improve for sure.
Okay, nice results. The mark, the grade is quite is positive. I mean, it's very nice. Thank you, Luminita.
Yeah, thank you.
Thank you. Now this is the end of this webinar. Thank you to all speakers for the presentations, and thank you for all participants for joining us this morning and for also being active on the chat. It's been a pleasure to spend this last event with all of you. Keep following us on our website and social media. The project will finish soon, but we still be active. The platform will still be live for many years, so we keep things going on, and please keep learning with e-SafeFood, and then we hope it was very interesting for you. We will send you a satisfaction questionnaire soon by email. Please send us your feedback and also what we can improve within this the platform, the content, the way it's presented, the way you can navigate in the platform. So we're happy to get your feedback. Well, thank you very much again, and have a great afternoon, and also enjoy your meal now. It's time to have a break. So let's say goodbye to all our participants, and well, keep following us, as I said. Bye bye.
Bye bye. Thank you.